Good morning. I want to welcome you all to the Younger Members Committee webinar, Assessing Safety, Search and Rescue, and Engineers' Role Following Disasters by John Lawson, who is at Cal Poly San Luis Obispo as an associate professor. We have some webinar protocols to share with you. You can open and close your control panel. You can join via audio, but all of you will be muted. So if you have any questions, please note that there is a button that you can press that opens this question area, so you can submit questions. They can be logistical, like you cannot hear or a slide is not showing, and EERI will help us deal with those technical difficulties. And also we'll take technical questions so that John can answer those at the end of his presentation. Also, today's presentation is being recorded and will be provided in the next few weeks via the YouTube channel. So I just wanted to introduce the Younger Members Committee, as we are the entity that puts on this particular webinar. It provides opportunities to early career professionals within EERI to advance their careers as earthquake professionals and become more active in the Institute. And I'm Anahid Baruzzi, and I'd like to introduce my co-chairs, Guillermo and Maria. So if you haven't already joined and you are a young professional in EERI, we encourage you to get in touch with us, and we can add you to our roster so you can participate in our activities, which are described on this slide. And you can email us at ymc@eeri.org. We also have a website where we keep things up to date on our activities, ymc.eeri.org. We also want to point out that we have a subcommittee under the YMC, and they are very active in assisting with post-earthquake reconnaissance. So those co-chairs are Erica and Manny. We do have a link on our ymc.eeri.org website if you're interested in participating in those efforts, where you can sign up, and Erica and Manny will coordinate with you on how you might get involved. So to introduce John Lawson, who is a colleague of mine at Cal Poly, he is a licensed structural engineer in California and Arizona. He has over 30 years of consulting experience in design and evaluation of buildings, master's degree from Stanford University, bachelor's from Cal Poly San Luis Obispo, where he's currently an associate professor. And why I was very excited to invite him to give this particular talk is because of his unique role as a structural specialist in FEMA's Urban Search and Rescue Program. So he's trained to advise these search and rescue teams in how to approach collapsed structures, and he's been deployed to earthquakes, hurricanes, mudslides, and the Oklahoma City bombing. And so he's going to discuss quite a few of those type of experiences, because a lot of times we as young professionals are familiar with the reconnaissance side of earthquake engineering, but we aren't necessarily familiar with the urban search and rescue side of things. With that, I will turn it over to John.
Thank you very much, Anahid, for that introduction. The picture you're looking at here I actually received about 2 hours after the earthquake occurred in Taiwan. And I was simply sent this picture indicating that it was a partial collapse of a hotel forcing closure of a nearby highway. And there were 4 questions. Can we search the upper floors? Can we operate at the base? We have search dogs. Where are the safe zones? And what do we monitor? And what are the decision points? And decision points meaning at what point when we see something we're monitoring go to the point that it's considered to be time to leave the area that it was too unsafe. These are the types of things that sometimes an engineer working in a sort of a second responder mode will be asked. And so what I'm going to be talking about today is when disaster strikes, what might happen instead of on the reconnaissance side, but really on the rescue side. And within hours, we have a program in the United States of urban search and rescue that is under FEMA. Within days, you may find yourself instead involved in a rapid safety assessment where you're tagging or putting placards of green, yellow, and red on buildings for the jurisdiction. And within weeks, you may be coming back and doing a follow-through and evaluating those tags further. So today's outline that I'm going to be providing is the first half is going to be urban search and rescue. The program that we have is really this immediate response by engineers. And then the second part was going to be this local safety assessment program under AC ATC 20, which is a rapid safety assessment, not necessarily looking for search and rescue, but to do a quick evaluation of buildings so owners and tenants can get back in their buildings knowing that they're safe, or staying out of the buildings until something else is able to come along and do a more detailed evaluation. So the Urban Search and Rescue Program that FEMA has, it's a national program under the Department of Homeland Security, and it involves certainly a lot more than engineers. It's a very large program that was born out of the Mexico City earthquake in 1985. That earthquake of an 8.1 magnitude had over 10,000 deaths, but it showed how the U.S. was probably unprepared for any heavy rescue that was going to be needed. Heavy rescue meaning large and movable objects. A lot of the local fire departments have the ability to do light rescue and medium rescue, but heavy rescue takes a high specialization of intellect as well as materials. The collapse of the Juarez Hospital in Mexico City had many live rescues that were of people that were trapped. In fact, I believe the last live rescue was after 10 days. And it showed that the need for a heavy rescue component to rescue people that were trapped was really needed in the U.S. And that's when it started, was 1990, the Urban Search and Rescue Program in the United States. Currently, there's 28 task forces across the U.S. You know, California has an abundance of these, mostly because of the earthquake hazards that we have with the population centers. Florida has 2, mostly because of the hurricane potential out there. And there's a number around the Washington, D.C. metro area because of the sensitivity of the government operations in that area. Now, with these task forces, there are a number of personnel all in a multidisciplinary role. We have, of course, the firefighter rescue components. We have the EMTs, search specialists, hazmat specialists, heavy riggers, and of course, the engineer will function in the structures specialist role. And there's communication specialists and logistical support. And they're all based usually around a fire department agency. And when we get deployed, there's a type 1 deployment, and that's really the full task force, and it's up to 80 personnel. And there's typically 2 structural specialists that are normally civil or structural engineers that are deployed with this task force. The task forces are usually about 3 levels deep, meaning that if not everybody is available, that there's certainly other people that can be drawn upon. So these task forces normally will have about 6 structural specialists on the roles for deployment, and they'll draw 2 from that group of 6. A type 3 deployment is usually a little smaller, about 40 personnel for something a little bit more limited, depending on the event, and they will send maybe 1 or 2 structural specialists on those. This is a multi-hazard response team. So not only are we multidisciplinary, but we also respond to multi-hazards. And of course, earthquakes is where the inception of the task force idea was born. However, we also respond to hurricanes and flooding, as well as tornadoes, landslides, mud flows. This is a picture from the Montecito landslide mud flow in Santa Barbara. Trench collapses, transportation accidents, explosions such as this grain silo where there was one employee that was trapped. Bomb blasts. This is the Oklahoma City bombing in 1995. And of course, terrorism. This was the World Trade Center incident. So the number of the more relevant deployments that these FEMA task forces have responded to are shown here. There's maybe about 9 earthquakes, both nationally and internationally. Hurricanes, about a dozen different hurricanes have been a response. Different blasts and terrorism, as well as some mud flows and landslides. Now, the role of the engineer in this task force, you need to understand that the work is being done in typically an unsafe building or an unsafe environment. And most will be multi-story buildings with heavy debris and potential for additional collapse. And the rescue and medical forces need to work in this environment if live victims are present. So the engineer is there really to help better define and help reduce those risks to the rescuers and the victims. We're not necessarily there to actually do the heavy lifting, but to provide assistance and consultation as far as what we might see from our perspective. And our hazard assessment would be essentially identifying maybe those vertical and lateral systems to start, as well as determining really where that load path is most vulnerable. Where is the critical load path, and where are we standing, and where's the victim relative to that load path, and what do we need to move out of the way to retrieve the victim that might be in the load path? Is it brittle or ductile behavior as we're working on the building? So do we have any forgiveness if we make a mistake or if there's an aftershock? We check for redundancy. Again, we're looking for safety to the rescuers and ourselves and the victim. And are the hazards something that can be mitigated to an acceptable level? Can we do it with shoring, or is there any toxic environment, hazardous materials that need to be taken care of first? Or is there a number of rats that are involved in some of the areas that have to be mitigated first before we can enter some of the environments? All these have to be taken into account. So as far as what the engineer is looking at is, what is this risk during the mitigation? We're going to be putting in shoring, possibly, and is it a safe environment to work in while putting in the shoring, or is it just considered to be unsafe until the shoring is established? And we're going to be checking for potential instabilities along the way, both in the building and the rubble. A lot of times the rubble is considered to be unstable, especially while removing it. It's always good to know where you are in the load path, because with the load path, if you are in a bad portion of the load path that is very vulnerable to aftershocks, you may not want to be there and working there. So the engineer's assistance for the rescue, once the victim may be located and be retrieved, you need to determine where the location in the condition of those voids may be. Our knowledge of buildings and building collapses, we may have a better idea where survivable spaces may be. Not only that, but if we know we have a victim or someone we're going to retrieve, we're probably in a better situation to predict what materials are going to be anticipated as we're trying to breach into that cavity. Are we dealing with post-tension concrete, or is it just simply standard concrete? Is that masonry hollow core, or is it simply going to be solid grout with reinforcement? And is this thin concrete or is this concrete topping we're finding on the floor, is it just an indication of a thin, lightweight concrete topping over wood, or is it actually something much more robust? And we can help provide assistance to the rescue crews as we see this. Where's the best access for search and rescue? Maybe our knowledge of the different materials and the types of buildings, we can direct them where the best direction for access to a void may be. So the skill set that an urban search and rescue engineer needs to have is certainly an in-depth knowledge of buildings and structures, the ability to identify load-resisting systems, know structural behavior under adverse loading, the ability to identify determiners of the structural condition. Is it going to be vulnerable to any sudden aftershock, or is it simply going to be fairly stable at that point? Certainly you need to have a knowledge of typical collapse patterns under wind, earthquake, and blasts. Now, don't expect everybody to have all the materials needed to do some of this rescuing on a standard fire department engine company. So a lot of this is going to be housed in a warehouse close to a fire station or within the fire department, and this cache is about $2 million of specialized equipment. There's special cutting tools, shoring and lifting materials, confined space operations. We have search cameras, listening devices. We have total stations that will monitor and survey different buildings for any movement. Search dogs, of course, medical supplies that are meant mostly to stabilize the patient for transport, as well as anything that might happen to the task force member. We have both global satellite and confined space communications, hazardous material monitoring equipment, as well as food, shelter, and water for 72 hours of being self-sufficient. This equipment needs to be transported, oftentimes over long distances. It's designed to be in a single military aircraft, say as a C-17 or 141, or split into two pieces on a C-130 transport plane. And theoretically, with a 6-hour notice, we should be in a wheels-up position, so the task force is usually ready to be deployed at any given notice, to be sent out to usually a military Air Force base or local airport if necessary. It can be pretty dramatic getting into one of these airplanes and realizing that you're simply knee to knee with our entire equipment inside the plane. Larger planes, such as this deployment by the LA County Fire to Nepal, was in a much larger C-17. Once we arrive locally on site, we are oftentimes transported by air to a stricken area if the roads are down. And our initial operations are in a sort of a blitz mode where we would conduct rapid structural triage in a multi-building event, trying to determine which buildings are the low-hanging fruit for rapid rescue. And this would be done with not only the structural engineer, but also with a rescue team manager and a hazardous material specialist. And we'd be doing some initial reconnaissance to start looking at where best to retrieve live victims. Afterwards, we would transition to a 24-hour round-the-clock mode where we divide the task force into 2 halves, 14 hours on and 10 hours off. So if we're in this rapid structural triage mode with multi-building incidents, we need to determine where best to start. We want to determine where the high priorities are. And the high priorities, we're going to be looking at where is a large occupancy that was likely during the event. And where would we find a collapsed building that has large survivable voids? And we have to consider how long is the time to access the victims. If it's going to be quick, it's going to be a higher priority. Hazards that can be easily mitigated must be considered, because if the hazards are going to be there during the entire rescue, that's going to be making it a lower priority as well. This is a form that we carry with ourselves. It's basically an evaluation form, a structural rating form that looks at the probability of any potential building having viable victims and assessing risk. Now, it's not really numerical. It's done really quick. We only have a few minutes to assess each building, and we need to come up with a structural rating so we can put these in a level of priority on this triage. So if we're looking at a building that has a collapse such as this after an earthquake, we want to know, well, what is the chance for viable victims? Well, it was an office building, and the earthquake occurred at 9:50 a.m., so we have a high potential for trapped victims based on the time of day and the use of this building. We also recognize it's cast-in-place reinforced concrete. That's going to make it more difficult to access the victims if it was a different material. We also have large spaces that are probably underneath these lower floors, because this is a lean-to collapse with open voids. And so when we look at our structural rating for possibility of viable victims, we would simply click the marks here and come up with a medium probability of viable victims. Now we need to assess risk. We look at the building, and we are looking at the fact that we have floors draping over intact concrete walls. That would probably mean there's a lower chance of further collapse, recognizing this building probably dropped some significant distance and landed in this position. The impact was probably much greater than we're going to have any time from this point forward. We also see, though, a lot of loose pieces of concrete hanging around, and each one of those is a potential death drop from onto the head. So we recognize that we have some falling hazards. There's a medium number of those that would need to be mitigated. And the lower floors probably have a robust concrete walls creating good void support condition. So we go back to our structural rating, and we go ahead and we rate the risk, and we just go ahead and give this a low risk. And now we move on to the next building. It's as fast as that. We have a chance to maybe walk around the building, getting a little bit of an idea, talking to people if we know of any live people that have been hurt or any knocking, things of that nature, but you can't spend too long in these large multi-building incidents. So we have a medium probability for rescuing viable victims with a low risk. This would be a recommendation only. Simply, I'm providing this to the task force leader. He can certainly overrule me. An example is if there's a school of children with maybe 5 of them trapped, that's probably going to have a higher priority than 100 people in an office building, simply because politically children tend to be always grabbing where the priority wants to be. Those choices are made outside of the engineer and more by the task force leader and the local jurisdiction. Something to think about when it comes to survival rates of trapped earthquake victims is it's so important to be able to rescue these people within the first day or so, because after the first day, survival drops very dramatically. After about 5 days, it's rare to find anyone live, but it has happened. Again, in Mexico City, they found infants in the Juarez hospital out as far as 10 days, and in Nepal, they made several rescues on day 5. Trapped victims from blasts have much less survival because of usually the effects of the blast itself. So in a normal operational mode, this is after the rapid structural triage, we will be assisting with the search. We'll be monitoring the structural safety of the building. We'll be reevaluating as debris is being removed, because sometimes the debris is actually providing strength to the damaged building. We'll also identify hazardous areas that are off limits. Then we'll be assisting with the rescue. We'll suggest access locations considering the material and the stability that's nearby. We'll be assisting in the shoring design that may be necessary to mitigate some of the risks. And we'll be monitoring the structural safety as the rescue proceeds. Security is always a concern. Everybody has a security ID tag. Many places that have had devastating earthquake damage, such as Haiti, the response was delayed due to security concerns that were on site. Our dogs are no exception. The dogs provide abilities to go into these buildings where there's potentially lots of hazards that were unacceptable for people to enter. And the dogs have an uncanny ability to locate live victims. These are special search dogs that are not cadaver dogs. They're not looking for dead victims. In fact, they're trained only to scent on live victims. Acoustic listening devices are a special tool that we have in our arsenal for locating people, as well as search cameras that can go into the debris with an articulating arm to be able to find if we have live victims in any voids. Now, the structural specialist, the credentials to be in this is you need to be a licensed professional engineer. And there are some exceptions for architects that are on some of the task forces as well. And you need to have a specialization in structures or an equivalent. You need a minimum of 5 years of engineering experience, including structural design and analysis, evaluation of existing structures, construction observation, and inspection. Also, you'll be required to complete a FEMA structural specialist course that trains the structural specialists in recognizing different collapse hazards as well as locations of voids. And this is conducted by the U.S. Army Corps of Engineers. And there's a lot of ongoing task force training that is required as well. In fact, this is a list of some of the ongoing task force training that my department requires, not only training in structural collapse and stabilization, but training in rapid structural triage and hazard assessment mitigation, structural monitoring and surveying with the total stations, ATC 20, which is post-earthquake safety evaluation of the buildings, and Rescue Systems 1, which is actually training with the firefighters themselves as a firefighter course where you're going to be learning all sorts of rescue techniques. Hazardous material, you're going to be in a first responder training situation for that, recognizing also confined space entry and rescue, not for the faint of heart who are claustrophobic, trench rescue techniques, weapons of mass destruction. We are felt that in a situation where it could be a biological weapon as well as a nuclear weapon, that we may be called in to act, and so it's provide safety for ourselves in those situations as well. We'll need to be learning basic crane rigging, aerosol transmission of infectious diseases, as well as learning the national incident response protocols that are done across the U.S. in a mutual aid type of scenario. We have ethics training as well as being CPR certified, first aid, and up-to-date immunizations for worldwide deployments. Ongoing training such as this is a rubble pile. We're learning access and stability issues and training on those types of situations. Here's a structural specialist from New England who's exiting one of the voids. We also learn high-angle rescue skills for pulling people out of vertical spaces, or if we have to actually descend ourselves into an area to provide shoring. And then, of course, the learning to monitor buildings with total stations. And these are able to detect the slightest of movements to determine if a building may be starting to become unstable, or if an aftershock has caused a building to become a little bit more out of plumb. There are various training facilities. This one by the Army Corps of Engineers is in Moffett Field, and it's sort of a disaster city type of scenario where they have both rubble piles, damaged buildings that are modeled, as well as confined spaces. We learn to shore and all sorts of modeling of disaster scenarios. Some of the shoring systems that we construct, we don't go out and pull out a calculator necessarily to design these. They are pre-designed with pre-designed load configurations in them. Each one has a special purpose that we use, whether it's a vertical shore or a horizontal shore. And these systems are all in what we have is a field operations guide, or FOG. The structural specialist has their own structural specialist field operations guide that provides information on shoring. This is an example of one of the shores that we can provide, and it provides additional ideas of how much capacity this system has based on how high the shore is and how to build these. And the firefighters all train building these shores. They don't necessarily have a good idea how strong they are, but they know how to build them. And as an engineer, we can direct them to build them, and we're simply also computing in our mind a rough idea of how much load it might need to take. Here's a shore that was installed in a earthquake-damaged building. We were worried about side sway collapse of the first floor, and it can provide a nice, strong vertical. So now we have a list of what is in this FOG. The Field Operations Guide has different failure modes of building types illustrated, as well as vertical and horizontal shoring, as well as repair techniques. Talks about signaling to crane operators, how to communicate the protocol with that. Some guidelines on how to operate the various pieces of equipment, such as the total stations, the GPS, how to use the GPS for tagging buildings to send to a follow-up rescue crew, and how to navigate through an area without roads or without street signs anymore that are visible. Laser range finders, rebar detectors, smart levels, material weights, capacities, knots, all sorts of great information. You might actually want to take a look at it. It's actually downloadable through a website, disasterengineer.org, and it is certainly available for you to peruse through and become acquainted with. Now let me give you an example of one deployment. This is the Northridge earthquake in 1994. The search and rescue task forces were only in a backup position for this event, but the Northridge Meadows complex, which was a 3-story wood frame apartment building, the first story collapsed, and there were 16 people that died in the number of buildings here. They were all on the first floor. However, one was rescued and survived that was found on the first floor. This is essentially how they would rescue through or retrieve victims, was through the second floor down through the first floor. Because the earthquake occurred at 4:30 in the morning, all the victims were pretty much trapped in bed. The death of the victims is typically by suffocation, as the weight of the building on them prevents them from breathing. And so it is not necessarily something that we're looking for broken bones or trauma. We're simply trying to get through as fast as we can above a location where a bed is. Now, an engineer, recognizing that these buildings typically have an 8-foot plate height, and as it is simply a collapse where it leans to one side, we can identify where the beds are by simply recognizing that these buildings have bedrooms that are stacking, and we find a bedroom upstairs, and we measure over 8 feet, and we know where the wall or where the bed would likely be located, and we cut at that location. So it's helpful for an engineer to look at the type of collapse, look at where the beds are most likely to be located, measure over how much translation occurred, and find the victims that way. Also in the Northridge earthquake, there was a victim that was in the Northridge Fashion Mall parking structure, and there was a street sweeper that was actually cleaning the building at the time of the earthquake, and he was rescued alive as well. Now, in the Mura Federal Building, which was in Oklahoma City, I was there for 6 days of the rescue operations. There were 11 task forces from the U.S. that responded. There were 6 at one time. It was a 15-day incident. And we had a total of 37 structural engineers that were part of the FEMA task forces at the location. This is a lot of devastation, but it's hard to believe there were only 4 columns that were compromised, that collapsed, and it created this type of partial collapse within the building. Also across, there was the General Records building, and really quite as far away as several blocks, there was damage. People died just across the street as well, so it was a multi-building incident. And you can see on the left, this was just after the bomb had exploded. Lots of hanging debris, very unsafe to work in this environment. In fact, there was a rescuer that was killed within the first 24 hours because of a falling piece of debris. This was not a rescuer of the FEMA task force system, but a local rescuer. On the right, you can see when we've cleaned up the debris and making the rescue and the search operations much more safe to work in. There's a lot of people on these incidents representing many different jurisdictions. And there is a lot of rubble, and the building safety could be compromised very quickly. You notice those columns on the right no longer have the 3rd floor attached to them, and so the slenderness of those columns are suspect, and we have lots of debris pushing on them as well. We monitor the buildings. These are some SMART levels that we look at, making sure that we don't have anything suddenly occurring. We have punching shear failure here from the blast. You see we had to put in some additional braces. There's a steel pipe brace coming in because of the slenderness of this column. Was just too risky to continue operations and remove debris adjacent to that column. We also had to repair some of the columns. You can see the steel jacket to the right with grout that's been put in. That's Dave Hammond, one of the senior structural engineers with FEMA IST, investigating some of the repair work there. On the left, you can see again these columns, very dangerous to work in this environment. We put in some shoring on the left, shoring on the right, so we can work underneath to retrieve some of the victims. Sometimes we're tunneling underneath to put in the shoring, and our cache actually has a lot of this wood with it, and we draw upon local resources as well. That's yours truly there, looking and actually tagging areas that are considered to be off limits because of danger. This is frightening, where an engineer on top or an operation working on top has no idea that all the tension steel has been ripped out of the bottom of the slab on grade, or the elevated slab during the collapse. And this lack of tension reinforcement made this whole area really off limits. There are some exceptional falling hazards in this. You can see that big piece of concrete hanging up near the top of the building. That was hanging only from a couple rebar, and the question came to the engineers, can we work underneath that? Well, we simply looked at it and said, well, it's about 20 feet by 16 feet roughly. That's 320 square feet. It's about 8 inches thick, 8-inch thick concrete. That's about 100 pounds per square foot. 320 times 100, that's 32,000 pounds. 32,000 pounds hanging. That looked to be pretty scary below. So we'll go ahead and go around the back, and only to notice it's hanging from a single rebar, a single number 8 rebar. We could look at the grade rebar from the ribs on the rebar. It was grade 40 because of the age of the building. A number 8 rebar is about 0.8 square inches times 40. Guess what? It's 32,000 pounds. We have the weight of the slab equal to the strength of this number 8 rebar. It did have 2 of them attached. You can see there's a disconnected piece of bar there, and one of the rescuers actually had cut the rebar thinking they would drop it and eliminate the hazard until it stretched that much, the remaining rebar, and they were worried about recoil and causing a secondary collapse in the whole building. So we had to live with this rebar and the slab through the incident, and we were not doing any rescue work underneath the shadow of that piece of concrete. We continued to monitor it by the Army Corps of Engineers. There were some high winds that we had to worry about, but these are the types of things that engineers do when they're looking in these environments. Everybody, of the 168 victims, only 2 were not recovered within the 15 days of our activity, but those 2 were recovered after the building was demolished because we knew exactly where they were. The World Trade Center, another deployment, even though it's not an earthquake, it was significant. Lots of damage. There were 24 task forces that were sent in. We were rotated in and out. Lots of people on this incident, but it was totally overwhelming. There were a total of 62 urban search and rescue structural specialists that participated in this event. And a lot of the work is simply looking at debris and monitoring it for hazards while they were simply working through and trying to retrieve victims. Large pieces that were potentially going to fall, we would monitor these with total stations, looking for any sudden movements or slight movements that would indicate that it was a dangerous place to operate. Lots of heavy steel debris made the work very difficult. Some of the steel sections were extremely thick, making it very difficult to move or penetrate. The local New York City Structural Engineers Association provided a lead on this type of work. Their high-rise engineers worked around the clock in different shifts. Thornton Tomasetti, LZA, was the lead engineer, but there was also work with Leslie Robertson's office, SOM, Wiglinger, as well as some others. There was also a special slurry wall basement that keeps the Hudson River from flowing into the basement of the World Trade Center, and Musa Redlich was the foundation engineers that investigated and monitored that. The Haiti response, another earthquake in 2010, nearly complete damage in many areas, and you think, well, we're not going to find very many people surviving in some of these pancake situations, especially when there's lots of loose rubble. However, there are exceptions where we would find this type of damage that someone could maybe survive in. There were a number of rescues. There was a lot of trapped victims that were found in these situations where we could retrieve. And as late as 1 week later, we were finding still survivors in these situations. And here's a woman being rescued out by the Search and Rescue Task Force. This is LA County's task force working there. More recently, the Nepal earthquake response. There were 54 task forces sent, but this was from a global response. There were 23 different countries, 150 canine dogs, 1,800 personnel. We sent 2 of our task forces from the U.S., which was 114 personnel, as well as 12 of our search dogs. Again, the Nepal earthquake, lots of damage with lots of rubble, not much in the way of survivable voids in some of these piles. The dogs can help find and scent on anybody that might still be alive. But there are some exceptions when you find some of these buildings that look to be reasonably intact, not necessarily searching inside the building, but underneath. The building seems to be fairly intact, and there's probably survivable voids underneath. The thing you always worry about, though, working in an earthquake is what is the risk of aftershock? And when we're making recommendations, we always have to think about what that risk might be. The USGS actually is able to provide numerical forecasts as far as what the aftershock risk is for different events in different parts of the world. This is an example from the Nepal earthquake that was issued about a week after the earthquake. And for that 1 week starting on May 1st, they provide us risks of aftershocks in that window based on a probability of occurring and how many might occur. An engineer can keep this in mind when thinking about that risk versus reward. If we know there's somebody alive, or if we just are simply searching for people that might be in a trapped space without any certainty of it, this has to be factored into the equation by the task force leader. In Nepal, there were a number of rescues. This is Fairfax County's search team in here in yellow hats working with the Nepalese in red hats. This was a teenage boy rescued after 5 days. He survived basically in a collapsed market by eating butter and was in good condition when he was rescued. This was a woman in her mid-30s that was also rescued on day 5 as well. So we don't give up hope out at a week. We hope we're still going to find people, and that's what we're trained to do. So when we get back to this collapsed structure, and I was asked, where can we search? A lot goes through your mind, especially when you're not there. But to give you an idea of what was done to quickly stabilize the structure, to allow it to stay in a reasonably stabilized mode, you can see the braces that the local jurisdiction put in to help keep this from moving any further. But an engineer could certainly provide guidance as far as where those braces should be set. And they should probably be set at the intersection of columns with beams with floors. You don't necessarily want to set this on simply a spandrel panel or something where there's maybe an empty stair shaft and you simply don't have anything strong behind it. Now, if you want to have something less intense to do, maybe you're not really looking for getting involved in something quite that extensive, you can become a safety assessment volunteer. And that would be simply being able to rapidly assess buildings as far as safe or restricted use, or whether they're just simply an inspected safe situation, unsafe or safe. And that is something that is very necessary so that people know whether to go back in their building. And this also was born sort of out of earthquakes in the 1980s. And in 1989, ATC 20 was published. And the idea is you do a rapid evaluation to determine whether it's a green, yellow, or red placard that's going to be tagged on the building. And if it's yellow, simply because it's questionable, it's going to be subject to a detailed evaluation later. So if we're looking at a rapid evaluation, you only have 10 to 30 minutes. You're typically on the outside of the building only, and you're going to be doing it either as yourself as an engineer or a building inspector or even architects are all working on these rapid evaluations. And sometimes it's the only evaluation a building will get. And the 6 key points that are typically looked at, it's like, has the building had any collapse or off its foundation? Is it significantly out of plumb? Is there any severe damage to any significant parts of the building that are important? Is there a parapet, chimney, or other falling hazard? Are there large fissures in the ground? Or is there anything toxic or any other hazard present? And you're simply spending a short period of time to evaluate these and post it. And then going ahead and post it, if it's questionable for future follow-up, it would get a yellow tag for a more detailed evaluation. And that detailed evaluation would be, again, for those yellow tag structures, which are going to spend some more time, a 1 to 4 hour time period, typically looking at interior also, as well as the exterior. And it's normally performed by a structural engineer or someone with expertise in that building type. And then that would be simply reevaluating that yellow tag into some other type of color, green or red, unless it's still undetermined, and then it would have to go on to a local structural engineer for further evaluation later. And ATC 20 provides guidance, such as places to look for the building type, whether it's wood or URM or tilt-up buildings. You know, you're going to be looking at some hazards as far as the panels falling away from the roof, or do we have cord failures, different inspection points to help assist the engineer evaluating the building. And these are useful for even students that are brand new, younger members of the professional communities to simply say, well, if I'm going to do reconnaissance, what should I be looking for? What are those things that are certainly easy things to spot? And the ATC 20 document is valuable for that. And a lot of these pictures have also been adopted into that field operations guide that the urban search and rescue people use as well. In Loma Prieta in 1989, it was really the first time that ATC 20 was used. It was really hot off the presses, and we were able to simply start posting these things. In fact, many of the jurisdictions had to simply make photocopies. They didn't have the colors yet because the document was so new and they were unprepared for it. With the Loma Prieta earthquake, there was a mutual aid response within California. The idea is that if San Francisco Bay Area has a bad earthquake, the local engineers will be too busy with their own jobs, their own clients, and that there was this sort of mutual aid response that Southern California and the Central Valley would respond in this time of need for the jurisdiction. And we were flown into the city of San Francisco. We were all deputized as city inspectors. We were given a vehicle, a driver, a radio, a list of addresses, a bunch of colored placards, the field manual, and recording forms, and we had at it and tried to cover as much of the city as we could. Obviously, we had lots of red tag buildings where people were very distraught with what had happened, people not able to get into their buildings anymore because they were red tagged and the police were keeping people out, and lots of damage with falling debris where people thought the building looked pretty safe to go into, but the falling hazards were just too great to allow anyone to go into. And we got to realize interactions with the people after these events can be very, very unique. During my work in San Francisco after the Loma Prieta earthquake, I was offered a couple times a bribe to change a red tag to a green tag. And essentially you had owners that didn't have earthquake insurance and they just simply wanted to go back in and not worry about the building. Or you had occupants that just simply wanted to go in and retrieve their belongings. In fact, there was one building that was demolished without ever allowing the occupants back in the building. Once you leave the building and it gets red tagged, it's going to be hard to go back in. I also had people trying to convince me that their green tag placard should be red tag placard. They wanted me to change it from green to red, saying that the building was unsafe. And really to get into the mind of what would cause someone to do this, well, you had landlords in rent control areas wanting to evict their tenants and reestablish higher rents. And you also had tenants that were desperate to move and wanted to break their lease. And so you find that working with people, you just simply have to do your job and move on. And you'll find that we do a lot of training in ethics in these types of scenarios and recognize that we have to just simply avoid that confrontation with people and inspect it the way we see it. Detail evaluations, this is just an example I borrowed from a presentation that was at the EERI's annual meeting in 2015. This was a building that was evaluated, and we find that the steel moment frames have local flange buckling at the joining between the beam and the column. And in fact, here you have hazardous materials that are stored in the building. It's an inside swimming pool, and you have local flange buckling at all these conditions here. You have local flange buckling indicating a significant weakness now in the structural system. But there was a lot of redundancy because there was a lot of it, a lot of these moment frames. So you open up your ATC 20 and you notice that there's something you need to be looking for is the distress at moment connections. And flange buckling near moment joints is considered to be unsafe for a posting. And so that would be a reason to post this building unsafe simply by the number of interfaces between the beams and the columns with local flange buckling. So you may be wondering, how can I get involved in the structural assessment program? Maybe urban search and rescue is not your cup of tea, but you'd like to certainly help as far as evaluating buildings quickly after a disaster. Well, you should be a licensed civil or structural engineer or architect or certified building official, and you have to complete the safety assessment program training to be an evaluator. And the training was originally established by the California Office of Emergency Services, but it's recognized now in many different states across the nation. And the ATC 20 training is about a 6-hour class. And once you complete that, most states recognize you as being certified to be able to conduct these types of structural assessment programs. There's also special training for windstorms and floods, which is ATC 45. The training is facilitated by NCSEA, that's the National Council of Structural Engineers Associations, and CEOC, and Texas and Washington State's Structural Engineers Associations, ASCE, AIA, and APWA, that's the Public Works Group, all have training or links to the training for this purpose. Also, I must mention that NCSEA has a structural engineering emergency response database that they're putting together. So if you are trained, they're trying to create a roster of second responders that can be shared with ICC, the International Code Council, as a single resource where people can be drawn upon after an earthquake. And our deployment in these situations are really there to assist the local government to tag buildings. So now if we're looking at additional resources that you may want to draw upon to take a look at some of the information I've mentioned here in today's webinar, disasterengineer.org is a clearinghouse location for information regarding some of the publications and work that engineers in the FEMA Urban Search and Rescue system will draw upon. So that might be an interesting website for you to look at. As well as California Office of Emergency Services has a number of links and information there on training. FEMA has a website on their Urban Search and Rescue program for some additional details, as well as the NCSEA's Structural Engineering Emergency Response Committee has some good information on how to get involved potentially on your local structural engineers group. That's pretty much the structural assessment program is done through structural engineering associations or the AIA, sometimes ASCE, and the urban search and rescue is typically through the local fire departments, with usually drawing upon some of the SAP evaluators, the structural assessment evaluators, for that purpose. Now, I've been with my task force here in California for urban search and rescue for about a little over 25 years, and there's 6 of us on the task force, and I would say about 4 of us have probably been there, and they're all 25 years. So there's not a lot of turnover in some of these task forces, and so it can be a hard position to sometimes obtain. A lot of times they're tied to different companies that have a specialization in reconnaissance and disaster management that tend to fund some or tend to have people on staff that can work in these types of environments easily. At that point, I hope you have found that the presentation has been eye-opening and not necessarily something that is reconnaissance, but sort of just before the reconnaissance level where you can get in and maybe serve a humanitarian purpose from a life safety issue. And I'd like to see if there's any questions.
Thank you so much. There is a really good question. What motivated you to become a disaster response engineer?
That is a good question. And it's funny, I wanted to do earthquake reconnaissance, and I was in a firm that was not necessarily able to fund my ability to do reconnaissance and structural engineering. It was a smaller firm. I had actually was looking forward to potentially do reconnaissance on behalf of EERI, but I was still a very young engineer, and so I thought, well, maybe I can get deployed to some of these locations by becoming a safety assessment volunteer. And within about a year of me signing up for the safety assessment program, the Loma Prieta earthquake happened, and then within a year of that, they were creating the FEMA task forces, and they asked me if I would join. And so that's how I got involved in it. And I would say just keep your opportunities open. If you think you've got your entire life planned and you have this roadmap you're going to follow, think again. Just leave your opportunities open. You know, keep going one direction, but always keep your eye open for something else that might be a divergent path.
Okay, I have 2 questions that are quite similar. I'm going to combine them. So the question is, what can be done to strengthen institutional and technical capacities for disaster risk management at national level or decentralized levels, and how feasible and pertinent is to involve societies in these activities? Well,
in order to it's government work is a very, very big institution and bureaucracy, and in order to strengthen it, it takes really a lot of stakeholders to have a champion, and the states have been very successful in doing this because the states have a limited geographic area, and they seem to have a very vested interest and their stakeholders. And so California Office of Emergency Services is great as far as developing a lot of these programs. And then, but FEMA, you're looking at a much larger animal, and it's very difficult at a national level to move quickly versus the local level. And so it seems to be best when it's working at the grassroots, at the local level, working up to the state level, and then FEMA creates the umbrella. But once FEMA starts dictating downward to what the local task forces need to do, there tends to be more resistance, and things tend to go much slower. The response on a local level, of course, it can be done very quickly, especially a state such as ours where we have a geographic area that's big enough that we can bring in rescuers from a non-stricken area. But if you're looking in the Washington, D.C. metro area, you're going to find that the rescuers themselves have family that are probably being affected. You have engineers who have clients that are being affected, and it becomes much more difficult. So FEMA's been very good at creating deployments that are in a mutual aid, a mutual benefit, reciprocity type of situation. And that has worked very, very well. And the training requirements that we've been getting lots of good funding so that we can have the task force trained and ready within a 6-hour window. I'm not sure if that answers your question, but maybe that gives you an insight at least on some of the institutional problems we have on having readiness.
Yeah, and I think this is going to be the last question. It comes from the academia. The question is, as a university professor, how do you prepare for the possibility of a sudden USAR deployment?
That's a good question because it was a lot easier when I was in private practice. I started teaching in 2009. So to get an emergency deployment, and I have a whole teaching schedule I have to worry about, can be a problem. Obviously, if it's during the summer months or during winter break, it's very easy for the deployment. So I essentially have myself in a backup position during the school year while I'm teaching. However, there are incidences that may, if they're too large, and the department has made ability for me to take maybe a week off if I need to. The deployment requires us to have 10 days. And if it's going to be more than 10 days, then we simply will cycle in another structural engineer. And so it's a 10-day commitment that we would have. But from my own personal standpoint, I will simply focus more on the summer when I am available and draw upon some of the other engineers on our task force to be deployed when I'm in a teaching mode.
Okay, I think this is all the time we have for questions. I'm going to pass to Anahid once again to the closing.
All right, she's going to be right here.
Thanks so much, John. It was extremely informative. I know he hit on a lot of things during his talk. So I hope some of you got some information about how to get involved and kind of what it takes and the impact that you can have. I just wanted to indicate that we did have some questions come in last minute, and since we have to close the call, we can hand those over to John, and he would be able to answer those via email. I guess we'll have to track down the email, or you can send it through the question window so we have your email as well. But any other questions, you can email to us at ymc.eeri.org. Or if you're interested in joining the Younger Members Committee because you are a young professional in EERI, we would love to hear from you and get you engaged in some of our activities. PDHs are available. More information will be provided in a follow-up email. And we just want to let you know that we have a post-webinar survey so that we can get some feedback from you on how this webinar went. And there's opportunities to make suggestions about what topics and what speakers we have in the future, because we are planning to have this be a quarterly YMC webinar through EERI. We already have a save the date for our next YMC webinar. This is going to be Dr. Abby Leal, Monday, September 17th, 2018, from 10 to 11 a.m. Pacific. So do put a note in your calendar so you can join us for that one. And we are excited to continue our webinar series, first one being with Dr. Sissy Nicolau with WSP, and the second one just completed with John Lawson from Cal Poly. So thank you so much for joining us, and I believe that's all the announcements that I have for today. So have a a good afternoon, and thanks again.